Okay, so in this bell work, I didn't put the poll up, so hopefully you just kind of read through it already. They are taking a sample. They're 1,000 high school students. They're not going to get all of them, so they pick a random number, and if it's 50, the person's included in a survey. Okay, let's see. Sorry, I lost my train of thought there for a second. But basically, after the survey questions, 30% said they couldn't live without instant messaging. So we're looking at proportions here, and we're going to construct a confidence interval. Have we met conditions? So is it random? Yes. These students were randomly selected. Is it 10% condition been met? Yeah, in fact, this represents only 1% roughly of the high school population in this town. So the last one is, have we met normality conditions? And for that, we need to make sure that we meet these calculations that are greater than or equal to 10. And we don't know the exact numbers, but we do know that 30% is the p-value, and with a sample size of about 500, we're going to have at least 10 failures and 10 successes. So we've actually met all conditions. I think the point of seeing this problem is that sometimes when you're asked this, the automatic assumption is that there is a problem somewhere and we need to figure out what the problem is. But be aware that the answer could be all the conditions have been met and a confidence interval can be constructed. And that's the case here. Be looking at units 3 and 4 today. We're going to have a little FRQ discussion. And first things first, we need to talk about the grades just a little bit more. I told you all the stuff that you're going to be expected to do from now through the end of the semester, but it's important to point out, especially for a lot of you in this class, I mean, a lot of students in general, but there are a number of you who might be totally happy with your grade, doing really well in class, and you might not want to be burdened with having to turn in all of these FRQs all the time. So if you do choose to turn in the FRQs, now these are optional. So is that practice test. Now, I highly recommend you go through them and look at them. But if you don't actually want to go through the effort of turning them in, because now I'm going to make you guys take pictures, and that'll come up in a second. But if you don't want to go through the effort of turning it in, or whatever the case, it's your choice. These are provided to help you boost your grade or give you a little bit of buffer as you are approaching the final and trying to bring that grade up as much as you can. But if you don't feel like you need to do it, it is optional at this point, and now in Canvas it actually reflects that. So you will not lose credit for not turning any of the optional assignments in, and they won't even show up in your student view. But turning them in will help raise your grade. Now, if you're already up higher, like already at an A level, it's not going to raise it that much, but it will give you those extra points that's going to help in your calculation at the end to buffer you against maybe if you don't do as well in the final as you hoped. So that's something to keep in mind, even if you're already doing well. Now, last night, all you had to do for the FRQs was turn in a little text document that said done. That it's basically a trust system that you actually did the work. But I decided I want to hold you a little more accountable. Now, last night is fine. If you turn that in, that's all good. But moving forward, I want you to take a picture of the FRQ. And if you need to if you need multiple pictures for it, then you can do that. There's a way of doing that in one submission. But anyway, submit a photo of the work you did in your FRQs, and that is going to be what you have to do for the homework assignments. Same thing for the practice test. If you're going through the 40 problems and you just write down your ABCs, Ds, whatever, all the way through, then you can just turn in that final thing with a picture of it. All right, and that is that. So let's talk about how you're going to talk about your FRQs a little bit. We're going to talk about how to talk about stuff. But if I just threw you into a breakout room, there might be a lot of silence. So I want to give you guys a little bit of guidance on what I'm hoping you guys talk about while you're in there. You should have looked at 2 FRQs last night. Unit 1 had specific instructions, but you're supposed to draw a histogram as part of it. So I want you to just describe what your histogram looked like, and you can show a picture of the histogram you created. This probably can be talked about and everyone can kind of share what theirs looked like in less than 1 minute. All right, so when you get in there and you're talking about the Unit 1 FRQ, just describe the histograms, show a picture. If you want to talk about the other questions, you can, but that's kind of one thing I want you to do. Unit 2, there's a part A and a part B. Part A had you calculate some z-scores. Part B had you calculate a different calculation, and you would have seen the problem if you looked at it. So I want you guys just to talk and focus on part B. Like, what was your process? What was your thoughts for how you approach part B? So when you go into the breakout rooms, please focus on just describing the histograms for part 1, sharing on your camera if you'd like, and then talking about part B for the Unit 2 FRQ. So that is basically it. If you didn't do the work, then you probably can still contribute. You could pull up the FRQ right now. You might be able to kind of reason your way through it real quick and see if you can contribute, or at the very least, follow along with what other people did. We are going to have these discussions every day, so I hope you guys are getting the work done, and I'll kind of guide what your discussion should be. Okay, I don't want to do a whole lot as a class with this, but I'm just going to do this. We had, I think, 6 different. All right, so we went all the way down from 20 up to 80. And, all the numbers in between. So what I want you to do, I do not want you to recreate your histogram for this. What I want you to do is just draw a line to show what your distribution looked like. So you might draw a line that looks like this if it was a normal distribution. You might, if it was a uniform distribution, you could just draw a line that's straight across. So just draw a line that represents what your histogram basically looked like. And anyone can do this. All right. Anyone going to draw just a rough idea of what their distribution looked like? So if it's skewed to the right, you might have something like this. Oh yeah, and you don't have to, well, that's fine. You can draw that just like that. That works. Okay, so you can see it follows something of a U shape. Okay, and that's very good. Thank you for that, Zach. And as long as you have that, you should be able to describe it. You might describe this as bimodal. It's fairly symmetric, but bimodal. And you could talk about the range and different things about it. But as long as you guys were able to kind of convert this into that, that's good. I'm not going through the full FRQ. Hopefully you guys had some decent discussion about it. All right, for the next one, again, we're not going to go through the full FRQ, but this requires calculating some z-scores and fun with that. But I just want to focus on part B. And we had the northern birds and we had the southern birds. I'm intentionally not drawing any numbers on this. And what I want you to do is I want you to mark, and someone can mark, it can be the same person, doesn't matter, but just someone mark where on the northern distribution would the 13-ounce bird fit? Like, would it be right here in the middle? Would it be, way over here? So someone draw where the z-score basically ended up, or something like that. Draw a line. There you go. So about right there is where the 13-ounce bird lived. For the northern, where would the 13-ounce bird exist for the southern distribution? Okay, there we go. So the z-score, we have a -1 for the south and a +1 for the north. And the question is, what's the probability of finding a bird greater than 13 ounces? So in the north, this is your probability. In the south, this is your probability. And just a visual like that, you might or might not have done that when you did your work yourself, but just to a diagram like that really shows the difference that you are far more likely to see a bird that heavy or heavier in the north, or sorry, in the south than you are in the north. Okay, and that's about as much as we're going to talk about with that. And now we're going to look through unit 3 and 4. We'll see if I skip over any problems here, but we got scatter plots and regression lines. We reviewed this stuff recently, so hopefully this kind of is already a little bit fresh on your mind with our linear regression inference. The equation of the regression line is an important part of this. This is something you might have forgotten. There's Duff's, which is if you're going to describe your scatter plot, you need to describe the direction. Is it positive or negative? Are there any unusual features like outliers or high leverage points? What's the form of it? Is it linear, nonlinear, and the strength? And you can kind of describe the strength in terms of the correlation, a strong, weak correlation, no correlation, perfect correlation in strange cases, moderate correlation. The correlation coefficient is that number that kind of quantifies it for us. And the coefficient of determination tells us the percent of the variation in the y that's explained by the variation in the x. So that's kind of our template for how we use the coefficient of determination. And it kind of tells us the strength of the relationship in a different way. All right, so in this one, we are looking at male and female lion cubs. And these two different samples are showing the relationship between average daily playtime and the age when they first hunt. And if we look at the males, it looks like no matter how much they play, they're basically going to start their first hunt at about 13 months. The females, however, they have more of a, it might be linear, non-linear, but whatever the case, there's a negative relationship. So as playtime increases, so I'll just put P for playtime, then time to first hunt, I'll put H for hunt, goes down. So more play equals faster time until they hunt. So the question is, which cub is more likely to begin hunting sooner the more they play? Well, the only one that has a relationship like that at all is the females. Okay. The next one, we have random sample of 20 professional athletes, linear, strong relationship. So it says that those who exercise more per week, so more exercise, tend to have lower resting heart rates. So I'll just put HR for heart rate. So again, a negative relationship. If we know it's negative, that means it's a negative correlation coefficient, a negative R. And so that means that we want to look for a negative value. It's a strong one, strong relationship. So I got a couple of strong relationships here, but this one is a perfect correlation. And this is very rare. And we typically don't see that. So it's actually one of those too good to be true kind of relationships. So the most likely outcome is this one. Now, if this had said, instead of strong, if it had said perfect, then of course we'd know what to do. We'd to pick that -1. All right, so in this case, we got a biologist collected samples of fish and was using their length to predict their weight. And all the fish varied from 0.75 to 1.35. And so he's got some measurements down here, and he wants to predict a fish that lives over here at 3. Now, this would be extrapolation, and that's above the maximum value in our data set for length. So we would not find it appropriate to use this model to predict its weight. Now, just a general kind of conceptual understanding about this, and we might have talked about it at the time, there's this great linear relationship we can find. But then once we extrapolate beyond it, extrapolating a little bit isn't a problem, but we get this cone of uncertainty. All right, and you might have seen this, we might have looked at this in terms of weather and stuff like that. We get this cone of uncertainty. So maybe like a prediction right here isn't too bad, but if we tried to predict way over here, it's like, is this some kind of a function that levels off? Or is this something that grows exponentially? You know, we don't know. So that's why extrapolation generally isn't good. Okay, So in this case, we've got an engineer testing a filter and how much pollution gets through. And so basically, if there is a linear model between these two, what would be apparent in the residual plot? I know I'm going through these somewhat quickly, but if you have questions, if you didn't understand the context well enough and you feel like I was rushing through, just stick around after class and we can talk about these more. So here's what an ideal residual plot looks like if it's a linear relationship. You're going to see no apparent pattern. So this is our best answer. We don't want to see any kind of linear association here, because that would mean that it would most likely mean that our least squares regression line was not correct. We would never expect all the residuals to be 0. And this talks about, we have a little bit of variability and then bigger. We don't want that situation either. We want it to be constant variation. Okay, in this one, we are making a prediction. We've got cows of 5 and 10 years, and here's the regression model for how much milk they're going to produce. So the predicted amounts of milk for a 5-year versus 10-year-old cow, well, you got two ways of doing this. You could realize that all I need to do is plug this in. So I could plug in 40.8 minus 1.1 times 5. And when we do that, we could get 35.3. And I could do the same thing for the other. I could do 40.8 minus 1.1 times 10. And I could get 29.8 right here. So you can just plug those in, get your answers, and figure out the difference, how that works out. And the cow of 5 years is going to produce 5.5 more gallons per week. This is the 5-year-old cow right here. This is the 10-year-old. And we can see that reverse that. So 10 and 5, or the other way around. There's the 5-year-old cow. This is the 10-year-old. Notice the 5-year-old produces 5.5 more gallons than the 10-year-old does. Okay, now that's one way you can do it. You could also recognize that it's just going to be, the difference is all going to be in this 1.1 times the difference. So if the difference in age is 5 years, then I can just do 1.1 times 5 and see that it's going to be a 5.5 difference. There's no best way of doing this. The best way is whatever makes sense to you. Okay. So this is a scatter plot with point A in there. And we're talking about influential points here. And just as a reminder, leverage means that it's got a difference in X values away from the cluster of the data. This one has a little bit of leverage. It's certainly, if we have our regression line without it right there, this is certainly an outlier from where we'd expect it to be. So this is going to cause this to change a little bit. So the dashed line represents maybe what the least squares regression line is with A. The solid line represents without A. Okay, so if we got rid of A, it looks like our slope would increase. So we can find right here. The slope increases right here. So that one's possible. Slope is unchanged. That's not true. Slope decreases. That's not true. The next one says increases and unchanged. So now we know that the slope would increase. Okay. But now would the correlation coefficient increase or decrease? So I'll just let you guys answer that one. What do you think? Would the correlation coefficient go up or go down? Okay.
Correlation coefficient increases?
It does increase. And keep in mind that an outlier, an influential point like this is frequently, but not always, frequently going to increase our or decrease the correlation coefficient, because we're going to see all these residuals when we compare it to the dang it. All these residuals will be much less if we were going with the original, with the line without the outlier. So if I compare that to the other residuals, notice that these points compact a lot more closely around the original regression line, and we just canceled that one out. So the correlation coefficient will be higher if we got rid of A. There's your answer. All right. All right, this is one where we're dealing with the coefficient of determination. It doesn't specifically say it, but in our answer choices, we've got questions that kind of lead toward interpreting the coefficient of determination. So when you have a correlation coefficient of 0.8, that means that your R squared value is going to be 0.8 squared, which is 0.64. So 64% of the variation in height of children is explained by their age. Okay, so if that's the case, we can find something that relates to that. Height is 80% of the age of the child. That makes no sense. Least squares regression line, height versus age will have a slope of 0.8. That's not true. Remember, your slope is, actually, slope is B. Your slope is going to be R times S sub Y over S sub X. So it's not just R itself. Proportion of the variation in height that is explained by regression age is 0.64. Well, that one looks good. The least squares regression line will correctly predict height based on age 80% of the time. There's no way of correctly predicting. I mean, you might get lucky, but this is to get kind of a prediction, but it's not going to be correct most of the time. So anyways, those are not correct. So basically the proportion of the variation in height that is explained by regression on age is 0.64. 64% of height differences are explained by age. Okay, and now we've got an FRQ on this. Just really quickly going through it, we got a cluster of data with this point P way out here in the middle of nowhere. And what this does is it artificially creates a pretty strong correlation. Notice we've got an R squared here, 47.6. So this initial analysis tells us that 47.6% of the data is explained by variation of study. So the variation in study is explained by the variation in work, 47.6% of it. But if you removed point P, if this was gone and you ran another R squared, you get 2.5%, which is practically nothing. And that makes sense. Without this, you probably have like a zero slope, no relationship. And the first question is, does this show that it's that it's an influential point? Yes, it does. We go from practically no association, no relation at all, to a fairly strong one. In fact, if we look at the correlation on this, that would be your 0.476, the square root of it, because that's R squared, so we can find the correlation, which would be about 0.7. That's a pretty strong correlation. And then when we go here, if we look at the correlation for 0.025, then we get it's basically zero. The exact numbers you could figure out. But we go from basically zero correlation to a 0.7 correlation just with 1 point. That's very influential. Okay, the next one. We are looking at the same scatter plot as before, but now they realize there was an error in how they coded it, and it should have actually been down here. So basically the question is, how would this differ? Now there's a lot of things you could say about how this is going to be different. Instead of a zero slope, the original data had, of course, a positive slope to it, but now we would expect a negative slope. So we're going to go from a positive correlation coefficient to a negative correlation coefficient. And, you could just say a lot of things about this. If you wanted to use Duff's to kind of describe both of those, you could. But bottom line, there's a lot of ways of answering this, and just try and put as much information about the differences between them as you can. And this isn't actually one that you have to do for homework, but if you look through this again and you want to kind of think through what you would put as your answer, you can do that. Okay, looking at Unit 4 now. This is dealing with sampling and experiments and observational studies, all that. So with sampling, there were the 4 main types we looked at: the simple random sample, cluster, stratified, and systematic. We also talked about the kind of bias that can come in. There's response or non-response bias. We'll talk about those. Undercoverage, convenience or voluntary response sampling. And all of this right here can just completely throw off the sample to be worthless for analysis. Sampling bias or sampling error or sampling variation, different names for the same thing, and probably sampling variation is the best name for it. This is not a bias in the true sense. This is a natural part of what happens when you take a sample. So in a population, there is a true value, right? And let's say that's mu. When you take a sample, you could end up with a sample right here, x bar sub 1. And then you do another sample, it ends up right here, x bar sub 2. Maybe your third one ends up pretty close, x bar sub 3. These differences between the true value and what your sample gave you is called the sampling variation or sampling error, and again, sometimes sampling bias, but it's not a bias. And you typically see it more as sampling error. Okay. So whatever the case, it's a natural thing. You can't get rid of it. So there you go. Observational studies. These can be retrospective or prospective, but in either case, there's no random assignment. You're just observing people living their normal lives. Experiments. This is where you do randomly assign people. You get participants. You assign the treatments, and that'll come up in a second. But before you do that, you might block them based on certain factors that you think might have an impact. So for instance, it's kind of like stratifying, but in an experiment we call it blocking. So you might block based on age, race, gender, even in certain cases based on non-physical characteristics like their religion and politics, things like that. So however you might need to block it is appropriate, or it might be appropriate for a problem. And then within blocks, you would randomly assign treatments and different levels. And one of those levels could be your control group, where if it's something like a placebo, not every experiment has a control group just based on how it's set up, but you could have a control also. I feel like there might be something else in here worth mentioning, but oh yeah. Experiments are the only one that can result in causality. Everything else, we cannot say anything about something else causing something else happening. So this is the only one where we can do that. Hopefully you remember all this fun stuff. And when we look at this, I hope that you're either having it all come back to you, you're saying, yes, I remember it, or you're saying, I don't remember it, but now I'm going to remember to go back and look at Unit 4. Okay, so we've got a teacher conference that's been happening, and lots of teachers from all over the state showed up, and 50 random conference attendees were sampled. And based on whatever question they're asking in the survey, where can you generalize these results to? And the answer here is that the sample is 50 conference attendees. So we already know where the sample is. The population we can generalize this to is basically only the conference attendees, because we don't know if there's a fundamental difference between teachers who do attend a conference and teachers who don't. As a teacher, I can tell you there's a difference. But anyways, we can only generalize this to people who attend conferences. Okay. So in this one, they're basically doing a survey to find out if students like changes that were made in a cafeteria. And so the person doing the survey stayed in the cafeteria for 30 minutes, randomly chose students to survey them. And then afterwards, this reporter showed that 89% was happy with the new menu. So of these statements, which is true? Now, just in general, basically what we're saying is, what we need to recognize right off the bat is that this is a flawed study. If students have the ability to go to the cafeteria or not, then this has what we call undercoverage in it. Because there was an entire segment of the student population that wasn't even included in the survey to begin with. They weren't even possibly included. So without reading everything, I just want to jump to the answer. This sampling by method is biased because it might not be representative of the entire school. And it doesn't say it, but it's undercoverage. Okay. So now we're looking at sources of bias again, which is the best example of non-response bias. Now, remember the difference between undercoverage and non-response. Undercoverage is this group wasn't even included in our sample frame. We couldn't even include them if we wanted to. That's undercoverage. Non-response is they were included, we included them in the survey, but they didn't respond to us. Okay, so let's just read through it. People might be uncomfortable with the survey question and as a result might not always respond to those questions truthfully. If you're getting any kind of response, it's response bias. Many of the people selected to participate in the survey who do not respond might have opinions different from those who do. Well, there we go. They were selected to participate, but they didn't respond. That's classic non-response. If we look here, people without telephones are overlooked. Well, this is undercoverage because they weren't even possibly included in it. The wording leads to people to respond in a certain way. That's response bias. And behavior of the interviewer leads people to respond in a certain way. That's also response bias. Okay, so your answer is B, or the second one there. A dog food company wants to test, and they're using an experiment to figure out if their new formula promotes faster weight gain. Okay, so puppies that were included in the experiment will be weighed at 1 month intervals, and they want to reduce the variability due to natural differences in puppy growth rates. And because it's an experiment, we're going to be blocking, not stratifying. So anything that says stratify, I can cross out right away. It's just a goofy stats thing. It's essentially the same thing, but stratifying is for sampling and blocking is for experiments. Now, between the two blocking regimes here, blocking on geographic location, that doesn't really make sense. I don't think geography explains that. So blocking on dog breed, we should be aware enough that different dog breeds grow to different sizes. So we would block on dog breed and randomly assign puppies to the different formulas within those blocks. There you go, that's the best answer. Okay, now we've got a florist trying to figure out if this powder she adds is actually helpful for helping flowers last longer versus water alone. So every single rose that goes out the door, she randomly decides if they're going to get the powder or regular water. And this is an experiment, so it's not an observational study. It's not a census. Now, it might be tempting to think of blocked, but we really didn't. We didn't separate these flowers into two groups ahead of time. And keep in mind, this blocking by type of water here, this is not a blocking. These are the treatments. So that would not be it. So we could have matched pairs design, but it's not really matched pairs. We didn't say these two flowers that are similar in these respects are going to be, given the different treatments. So it's a completely randomized design. Even though it's a flipping of a coin, it's still completely random. We don't know how many are going to get the one treatment versus the other. Though it will work out to 50-50, more or less. Okay, now in this one, we had a bunch of fertilizers being tested. And right here, it tells us that 200 green bean seedlings were planted on identical plots. And basically, they ran through this experiment. And they found the mean weight of the seedlings and determined how effective were the different fertilizers. The scientists concluded that the new fertilizer was more effective than the other fertilizers for all vegetables. Why is the scientist's conclusion not appropriate? The experiment only included green beans, so we cannot generalize this to all vegetables. All right, so there's the problem in their conclusion. Again, I'm not spending tons of time, so if you need to spend more time coming back to this, you can. Here's the FRQ, and you hopefully remember these. Hopefully you remember a lot of the stuff we're going over. But in this case, we have all these participants in a survey, or in an experiment, that is. But this is on shampoo, and we want to, we could theoretically just give 6 random people a new formulation, and the other 6 the old formulation. But the company believes that based on age, people's hair will be different. So they want to block in size 2 for the experiment. And if we wanted to block based on age and give the old and the new within the blocks, then maybe we could take the 2 youngest that are right here, give one of them old, one of them new. This would be randomly assigned. Go to the next 2 youngest, which are these 2. Again, randomly assign old or new. The next youngest are, it looks like these 2 right here, and then randomly assign there. And then you can keep going. So here are the next youngest, and then these guys, and then these guys. So you got your 6 blocks right there, and you would randomly assign within each block. Now, the company might also decide that, you know what, it's not just age, it's also gender that determines things. So how would we design a blocking regime for this setup where we want to factor in gender and age? So in this case, if I just looked at the males, first of all, and then I could find the 2 youngest males, which would be these 2. And then I could find the next 2 youngest males, which would be these 2. And they're fairly close in age, so they block together well. And then these 2 guys. So there we go. Now we came up with those. We could do the same thing for females. And that would be appropriate. The last little bit says, using the blocking scheme that we just came up with, the boss suggests giving 3 blocks the old shampoo and 3 blocks the new one. But remember, we want to randomly assign within the blocks, not between the blocks. So that would not be appropriate. So there we go. Quick overview. You've got a couple of FRQs tonight. If you want to turn them in for credit, make sure you take pictures and upload those. We're going to just look at Unit 5 tomorrow since it's a shorter day, and work on the practice test if you would like. Bottom line, that's all we have for today. If you don't have any questions, you can have a wonderful day, and I'll see you tomorrow.